Okay, so this is like some of the first shear force and bending moment diagrams that we're going to do. So let's go through these slowly and make sure we understand the process. So let's look at the one here on the left first. It's a cantilever beam with a load P at the end at a distance L. Just to save a little time, I'm going to go ahead and tell you what the reactions are on the left-hand side. You can probably see them anyway. If you sum forces in the y direction, you can see that I'm going to get a force that reacts up and has a value of P. And you'll also see that if you do your moment, you'll find that the resulting moment is a negative bending moment with the value PL. Again, if I gave you a little extra time, you could find those very quickly. So let's take what we know and draw the shear diagram. So just to remember, I'm going to write here to remind you that the change in shear, remember, is the area under the load diagram. And then also that the slope of the shear diagram is equal to the load. So those are the two relationships that we're going to use to do this. So starting at the left-hand side, what's the shear? A force acting up on the left-hand side. Is that positive or negative shear?
Positive.
That's positive. So I should start at positive P. Now when you look at this piece here, what should the shear at the end be? That's a little maybe more challenging to see. So what I want to do real quick is just draw a little simple free body diagram of that section and kind of show you. So if I take a really small slice, say a differential slice of the beam, and on the right hand side is the actual load P applied. On the left hand face here, positive shear is up or down? It's up. Look at the equilibrium of that little piece. What should the shear be? P, positive P or negative P? Positive P. So that means that I should also hit positive P on that side. So what's the change in shear between those 2 points? It's the area in the load diagram. What is the area under the load? 0. So that's great. If I start at P and there's no change, I should end at P. And what's the shape? Well, the slope of the shear diagram is equal to the load. And the load is 0. So here's a curve with 0 slope, which says that this structure has constant positive shear throughout the whole length. Okay? Any questions about that? So let's go to the next piece. So we now know that the change in moment is the area under the shear diagram. And then of course, the derivative relationship would be that the slope of the moment diagram is given by the value of the shear. So let's again start with what we know. Okay, do we know anything about the moment on the left-hand side? Well, sure. What kind of bending moment is that? Positive or negative? That is a negative bending moment, right? So we're going to start off at minus PL. What is the bending moment at the free end? 0. So our relationship says the change in moment is equal to the area under the shear diagram. So let's look at the area of the shear diagram. It's a rectangle. That's easy to calculate the area. It's just base L times height P, and by the way, that's a positive area. So it should be positive PL. So if I start at negative PL and I add the shear to it, I get 0, and that matches. So what's the slope of the moment diagram? Well, it's equal to the shear. And the shear starts off positive, P, and does not change. So it's a constant slope. And a constant slope is a straight line. And there's your moment diagram. Now, if you just review what we talked about, you'll notice they're almost outside of this where I told you what these values would be. There'll probably be some calculation for that. Some forces, some moments. But you see any calculations here? They're all pretty simple. You're done. That's it. Pretty cool, huh? What's the likelihood you would get this problem on the exam? 0. Well, we have to start somewhere, right? What about this guy? What's the difference over here? Yeah, so let's see. What would be the reaction? What would be the shear reaction? Some forces in the y direction, you get nothing. What would be the moment reaction? It would be this direction equal to m naught. So what's the shear at the left-hand edge? Right here. It is 0. What's the shear at the right-hand edge? 0. The change in shear is equal to the area in the load diagram. What's the area in the load diagram? Nothing. The slope is equal to the load. What's the load? 0. So 0 slope. So this beam, believe it or not, has no shear. So let's go to the moment diagram. Do we know the moment on the left-hand edge? Yeah, it is m naught. Is that positive or negative bending moment? That is positive. Do we know the moment on the right-hand edge? Yep. Is that positive or negative bending moment? Positive. So I know where I'm starting, know where I'm ending. Change in moment is the area in the shear diagram. There is no shear diagram, so there is no change in moment. That works. And the slope of the moment diagram is equal to the shear. What's the value of the shear everywhere? 0. So that means everywhere our slope of our moment diagram is 0. So this is the case where we have constant bending moment throughout the whole cantilever. Now, before I leave this page, let me just add one little quick thing. If I applied a moment like this, how do you think this beam would bend? Would this tip in, the free end, move up or down? It would probably move up. So you're probably looking at a deflected shape, something like that. Exaggerated, but something like that. What does that look like to you? Is that happy or sad? Happy. It's happy. So you see we got all positive moment. What about this side? What's this one going to do? Is this tip going to go up or down? Probably going to go down, so you would have a deflected shape that looks like that. And you'll notice that curvature is negative. We have all negative slope, all negative bending moment. Yes?
Can you explain quickly again about the moment for this one?
On the right-hand side?
Yeah, because I thought you said that.
Well, when you twist this, if I twist this, is it going to go that way or that way? Yeah, it's going to go up, so it have to bend like this. So what does that look like? That's positive curvature, so you have positive moment, bending moment.
Yes.
Compared to this side. Now when I push this down, hopefully you can see that yeah, that's definitely got to bend like that, right? And that's negative. Everywhere it's negative, so everywhere the bending moment is negative.
I guess I'm confused. Why would the moment on the left side of it, why wouldn't it be at 0? Why would it be at positive?
You mean right here? Well, it's the reaction. Right? If you sum moments about this point here, you'd have to have a reaction moment equal and opposite to the applied moment. So you're without a reaction, what would happen to your structure? It would just It would just spin, right? So you got to have something equal and opposite to keep it from moving. If you look at it, you might remember that this is the way we define positive moment on a section with moments in that direction on each side. Okay, cool. So we did